Okay, so in the previous video, we learned the basic structure of estimation. So the idea was that we have a population. The population is just everyone we'd like to know, but we cannot. So we only observe just a part of the population, which is a sample. And what we want to know is a parameter, which is a numerical description of the population, which can be a mean, variance, probability, median. Like those can be a parameter, but we don't know the parameter unless we observe infinite number of everyone in the population, which is impossible. So instead, we observe the sample. So from the sample, we calculate something. The something is a statistic, and we are going to use a statistic as an estimator for the parameter. So basically, we have a parameter and a statistic. So the parameter is what you want to know, and to answer this question, we have a statistic, and we use a statistic as an estimator. So, and the basic minimum requirement for them is a parameter is what we want to know, so it must be fixed. It should not be random. If it is random, that means the answer is moving around. The target is moving around. It's not good. On the other hand, an estimator must be something that's tangible, that is calculatable. So you should be able to calculate an estimator from the data. So based on this really basic setup, this applies to any statistical inference. Now we are going to think about what is an estimator, like what is a good estimator. How can we evaluate an estimator, right? So to do that, first we have to understand that an estimator you calculate from the sample is random. That's the starting point, right? So remember, a sample is generated from an experiment called the random sampling. So we survey 1,000 people. That is one experiment, and we calculate something from there, right? Like you can calculate the mean from the sample, or you can calculate the standard deviation, the median, the probability. Whatever you calculate from the sample can be an estimator. It can be an estimator, but the evaluation is based on its probability distribution. Because it is random, it may be wrong, it may be correct, but first thing is to think about the randomness in the estimation procedure. So the perfect estimator will be like this. So we hope the estimator you calculate, so theta hat is what you calculated. I hope this equals the parameter I'd like to guess. So it's theory, so we are in our theoretical analysis, we pretend as if we know the truth, right? So just for analysis, of course, in our real data analysis, we don't know where is the truth, but for now, assume that theta is the true parameter we'd like to estimate. So we hope what we calculate equals the true value we want to know. And we hope that equality holds with probability 1. So the probability that your guess is correct should be 1 if your estimation is perfect. Of course, it is impossible. If this is true, that means basically it means you always know the truth, so you don't need statistics. Okay? So this is impossible, in the world of randomness. So it is impossible. So we have to think about more realistic distribution. At least what we know is that we learned that sampling distribution is a normal distribution, right? So sampling distribution will be approximately normal. So it will be something like this. Suppose that your true parameter is here, then your estimator will be somewhere around the true parameter, more likely to be correct, less likely to be wrong. The probability of the error, probability will go down as the probability of larger error will be smaller, right? The tail probability goes to 0. So larger errors are less likely than smaller errors, desirably. So this is what we want, and typically this is what you expect from the distribution of estimator relative to the true parameter, right? So based on this distribution, we are going to think about criteria, how to like evaluate, assess this distribution, how good this is. Like to think about that, we are going to think about estimation error. So like this is a distribution, blue is the distribution, but like what you observe is just one realization. You are going to calculate something, one like you are, it's like drawing like rolling dice. You will get one outcome out of this distribution, and say suppose that you happen to be here, your estimator is calculated to be here by randomness, then your estimation error will be this much. So the sampling distribution of the estimator relative to the true parameter is basically, you can view this as a distribution of the estimation error, right? So this is estimation error if your estimator happen to be here. But if you repeat the estimation like with a new set of data, then you may get another value. Like you can come down to here, or maybe here, or can be more correct. It's random, right? It's like everything is random. Then, so now we just saw that the distribution is, you can understand the distribution as the distribution of estimation error. So then, like we may interpret the distribution in many different ways. For example, your estimator may fall on the right hand side of the true parameter, which means your estimator is greater than the true parameter, which means overestimation, right? You are overestimating the true parameter. So then the area on the right hand side of the true parameter is the overestimation probability, right? So it happens, right? So this is that probability. You may understand it this way. Similarly, also you can think about underestimation probability on the left-hand side of the true parameter, right? Left-hand side is the underestimation. Estimator is smaller than the true parameter, so the area is underestimation probability. Or you may wonder, you may like, this is another interesting thing. What is the probability that the error estimation error is within a certain radius, right? What is the probability that error is smaller than certain value? It's like an interval around the true parameter. So you allow a certain margin of error. What is the probability within that margin, right? Around the true parameter. You can calculate this area, right? That is normal distribution, so this is possible, and we are going to do that later. So understanding the sampling distribution is really important to understand how good your estimator is, okay? So now then, you can compare. So what we are doing is, we are going to compare two different estimators, right? You have two different estimators, which means you have two different sampling distributions. Like, for example, you can imagine, like blue is the sampling distribution of the sample average. And suppose like orange is the say sampling distribution of the sample average after deleting outliers, right? For example, then they will have different sampling distributions relative to the true parameter. True parameter is always the same, right? It's fixed, but they have different, like different estimators will be different. Will have different sampling distributions. In this case, we can conclude that like the problem is that the orange has a problem because it tends to be greater than the true parameter, right? So orange method, orange estimator is more likely to overestimate than underestimate the true parameter, right? So blue is kind of fair, like unbiased, right? It's like overestimation probability is 50%, underestimation probability is 50%, which is the best we can think of, because as much as you overestimate, you underestimate, because yeah, right? But in the orange case, it is more likely to overestimate than the underestimation. So that is a problem. It's not balanced. Okay, that's one possible way, one criterion we are going to use to evaluate on, like to compare to estimators. And another possible criterion to compare the estimators is that in this case, blue and green are balanced. Both are balanced in terms of underestimation and overestimation probability. Both are like centered around the true parameter. But the problem is the probability far away from the true parameter, right? So what you can tell here is blue has more probability near the true parameter, which is better. But the green has more probability outside of the true parameter. So green tends to have larger estimation errors because it can be like a value outside of the like far away from the true parameter. So more probability is closer for the blue, so blue is better. Like in this case, it's about variability. Okay, so these two are the basic ideas behind our criteria. So one is about, simply speaking, this is about the center. Orange has a wrong center. It's too large overall. And second, it's about variability. Green is too variable, too much variable, so it's not reliable. You may have larger error than the blue. So in these two cases, in these two criteria, it is pretty sure which one is better. So we are going to formulate this idea to using more like a simple measures. So this is the idea. First, I just mentioned, it is about the center. We want the expected value of the theta, the estimator, theta hat. We want the estimator to be the true parameter expectedly, right? So on average, it is correct. Sometimes it overestimates, sometimes it underestimates, but overall, they cancel out each other. So the expected value is correct, right? That demonstrates this comparison. Okay. Second, we hope the variance is small. The variability of the variance is small so that like it does not have larger errors and it's more stable. Even though the data are extreme, but I want your we hope the estimator take care of the outliers and give us better, like more stable, more reliable results. That's the second criteria, right? So we know we have the basic criteria here, but this is actually easier said than done and in practice, because theoretically we can imagine like the true parameter is somewhere there, but in practice we never know where is the true parameter. So, and in our imagination, we think about the randomness. It's like the estimation can be repeated, so we have sampling distribution. But in reality, we do not repeat. We cannot repeat estimation a problem. Like we cannot repeat random sampling at all, right? So we need to study this theoretically. Analytical method is enough to think about these two criteria. So it requires your imagination, right? So let's think about the first criteria first. The first criteria is called the unbiasedness. So as I said, the difference between your estimator and the true parameter is the estimation error. It is random. And if it is positive, it means overestimation. If it's negative, that means underestimation. And we are going to calculate. So like errors always happen, and it's either positive or negative. But what we hope is, on average, the expected value of the estimator should be 0. The expected estimation error should be 0, right? If it's not 0, we call this the bias of the estimation. So if the bias is positive, that means this is overall positive. Like positive side dominates the negative side. So it's more likely to overestimate, tends to overestimate. In the other case, if the bias is negative, that means the estimator tends to underestimate the true parameter. So neither is good. What we hope is the bias to be zero. We hope the bias is zero, and then we say the estimator is unbiased, right? So this is pretty much minimum criterion, or like we would like to utilize, like we would like our estimator to have, right? So as I said in the previous example, the orange tends to overestimate too much, so it is biased. It is biased, positively biased. So then you like when you compare blue and orange, I say blue is strictly better because it has zero bias. It's unbiased, which means the center is correctly at the true parameter, right? The center is correct, right? So it's distributed around the true parameter correctly. Okay, that was pretty much straightforward. We want like the center to be the true parameter. The second criterion is more tricky. So it is about variability, so which is about standard deviation, right? We'll think about standard deviation or the variance. As I said, we said like so. Standard deviation of an estimator is often called the standard error, right? So standard deviation of estimation error is standard error, right? So standard error is like interchangeably used as standard deviation, but more rigorously, standard deviation is more general statistical term, but standard error is specific to an estimator. When you estimate something, its standard deviation is standard error. Whatever, anyhow, it is standard deviation. We want standard deviation to be small because when you repeat the estimation, for example, like there are several research centers and they survey different people. So if you apply the same estimation method to different data sets, what we want is those results are similar. We hope the results are similar even though the data sets are different, right? So it's more about like stability, consistency, reliability, right? So that is reflected on the standard error. If the standard error is large, that means if you use different data sets, like and you apply the same method to different data sets, the results may be totally different, which is not good. You cannot interpret what is going on. But if the standard error is small, that means you apply the same method to different data sets, they are going to be similar, right? So small standard error is better. And what is interesting is the name for the criterion is efficiency, right? I think reliability is a little more like suitable term here, but I don't have that power. I cannot change the name of the theory. So it is said the estimator is more efficient if the standard error is small, right? Like think about this. There are two estimators, two candidates for the estimation problem. And if one estimation method has smaller standard deviation than the other, then we say this is better, and which we say more efficient. A smaller standard deviation means more efficient and better estimator. And exactly this reflects this idea. Blue is better than green because more probability is closer to the true parameter, right? So that is reflected on to the standard error. Okay. Now let me explain a little more statistical intuition behind it, more theoretical statistical intuition. The reason why it is called efficiency is because the efficiency is determined by the sample size, right? So remember, standard deviation of x bar, the sample average, is calculated this way. Single outcome standard deviation divided by the square root of n, right? So, so the larger the sample size, the better your standard error is, the better your estimator's efficiency is, right? Your estimator is more efficient if you use more data, right? That's then like if two estimate, then you may think like this. There are two estimators. One estimator has smaller standard error. That can be interpreted as the other estimator is not fully utilizing the full sample size, right? In some sense, the sample size is not fully utilized, so like larger standard error can be understood as is an equivalent to smaller sample size, right? So it's like you may understand the efficiency as if, like, given the sample size, if you efficiently use the sample size, you should be able to minimize the standard error. Like larger sample size minimizes the standard error. Like if your method can minimize your standard error, that is equivalent to having more sample, right? So in that sense, we say this estimator is efficient, right? For example, like this is the standard error, like for standard deviation of sample average. But if you compare sample average to median, so suppose that you are comparing median and the sample average for an estimation problem, which is better, at least in terms of efficiency, sample average is better because approximately the standard deviation of a median you calculate from the data is larger than the standard deviation of the sample average. Sample median has larger standard deviation, so less efficient. So this means you may understand this much difference as a kind of loss of sample size. Like, so this to cancel this out, you need to have larger sample for median. So it's like it means you cannot utilize the given sample size efficiently. So then, a simple summary, super simple visual summary. So we learned two criteria, bias and efficiency. So unbiased means your center when you shoot, like, so it's like estimation is like think about estimation as a guessing game or a shooting game. So you'd like to shoot at the goal, like the bullseye, right, at the center. Here, true parameter is at the center of the target, right? But you cannot always hit the bullseye. Like your shooting results will be around the target. When your shooting like mechanic is unbiased, that means your outcomes will be centered around the true parameter, right? This here is centered around here, and this also centered around here. On average, it may deviate to the right or to the left, above or below, but on average, it's centered correctly, zeroed in at the true parameter, right? Unbiased, if your mechanic is unbiased. But if your shooting mechanic is biased, that means if your gun is like biased, it is centered somewhere else. It just deviates overall. The center is not exactly at the true parameter, right? So, like it's too much like a left bottom. And here in this case, it's adjusted, like it should be adjusted, like it's centered too much like a top right, right? So it deviates, like it's totally targeted at the wrong point. It's zeroed in at a wrong point. So your estimator is going somewhere else, right? The other dimension is efficiency. Efficiency is about, stability, how much it varies, like from time to time. So first, your first shooting and the second shooting they are close to each other, which means I don't know how to describe it in shooting. Like it's stable, reliable, and does not have much vibration or like that. But if your gun is not well maintained, like or has some mechanical problems, some like from time to time it's scattered around. It's too much different, so you don't know where to aim. Like it's just even if you aim at the correct point, it's deviating from the true parameter, so it's inefficient in that sense. And then you may compare like this. So this shooting results is on like it's biased. It's not correctly aimed at the bullseye, but it's at least it does not have vibration. It's correctly going to hit the aimed point. But the aim is not correct, right? And this is the worst possible case. Like it's not correctly aimed and the results are not stable. Like it's not going exactly at the aim. So your estimation problem can be understood like this, and based on these simple criteria, we can tell which is a better estimator, which is a good estimator. In statistics, there are more criteria based on different aspects of the estimator. I'm just introducing the two most basic ideas. Okay, so let's apply this idea. First, if you are interested in the expected value, true mean, right? So like we are curious about the true average income in the United States, and usually we denote it as mu. Expected value is denoted as Greek letter mu, and then simply the conclusion is the sample average. Calculate the sample average to estimate the true mean, true expectation. It is a good estimator because we know it is unbiased. We learned it last chapter. In the sampling distribution, we learned the sample average's expected value equals a single outcome's expected value, right? Which means your sample average is unbiased. Expectation is correct, right? And standard error, we know the standard deviation of the sample average is single outcome standard deviation divided by square root of n. And this is like there are mathematical theorems that show that this is the minimum possible standard error among regular estimators. Under certain conditions, this standard error is the minimum possible, which means your sample average is the best estimator in terms of unbiasedness and efficiency. Okay, so we call this like minimum variance unbiased estimator for the mean. Again, so when you would like to estimate the mean of something, just use the sample average. That's simple conclusion. There is more mathematical theorem behind it, but I will just keep it as simple as this. But you just get the idea, and whenever you need to estimate the mean, use the sample average. That's what you have to take away. Okay, there is no better unbiased estimator than the sample average. Second example is like estimation of variance. So often you are curious about the variance, like variance of stock price, variance of income, which is income inequality, variance of like test scores, something like that. So we need to estimate the variance in some cases, in many cases. And in chapter 4, I suggested two formulas. Population variance formula that uses n in the denominator, and sample variance formula using n-1 in the denominator. And at that time, I recommended the sample variance formula, and I promised I'm going to explain that in chapter 8 now. So the reason why we use the sample variance formula is because it is unbiased, but the population formula is biased, right? So if you calculate the expectation of the estimators, then the population formula, which the formula itself is more natural because it is the natural average, right? Some n number of square deviations and then divide by n, but it results something other than what we want. So we would like to estimate sigma squared, which is a true parameter, but it's not just true parameter. It is multiplied by something else. So it is biased. So the population variance formula underestimates the variance. To fix that, we have to use the sample variance formula. It is correct. It is unbiased, right? This is why we use the sample variance formula, and it satisfies the unbiasedness criterion. Okay, thank you for watching. In the next video, we will start a new topic, confidence interval. Okay, see you later.